Hey y'all, welcome back. It is your radical math teacher, Mr. Boyden. I'm back at it again today. We're doing part 2 of the integral series, okay? So today we're going to be talking about analytic approaches to solving them, as well as definite and indefinite integrals, okay? So let's get right to it. We already learned how to do derivatives. The easiest way to think about what an integral is or an antiderivative is, it's just the opposite. So it is the minus that completes the plus. It is the divide to the multiplication, okay? So we've just learned a new operation. Derivatives are the new operation. Antiderivatives, or integrals, used synonymously for now, is just undoing that, okay? And so the way we write that, if you took a function and you took a derivative of f, what would you call that? Hopefully you would call that f prime, okay? When you go the other direction, when you take an antiderivative, or you underivatize, you get a capital F. Now, you may have thought that capital and lowercase letters were really only for proper nouns, and you really only had to pay attention to those at the beginning of a sentence. Nevermore, okay? It is now a math thing. The capital matters, okay? It means something different. So you do need the capital to denote the antiderivative, okay? And so if you integrate, you get an antiderivative. Okay? If you take a derivative of an antiderivative, look at this, that's capital F, so that says it's the antiderivative, and I'm derivatizing it, then I get back the original function. Okay? So with that, let's get into a little bit more specifics and a little more vocab. Okay? First things first, we need to know the difference between definite and indefinite. In the definite case, it finds an area, we have bounds. Okay? It goes from 0 to 7. In the previous video, we went from 0 to 3. Okay? So we've already done this. We've done examples just like this. Okay? In an indefinite case, it doesn't have any bounds. That's why it's not definite. It's not defined. Okay, so there's no bounds. It can still be the same f function. And so in that case, all we're doing, it's a command. We're being asked to find an antiderivative, not an area. Now, it turns out it's a little bit less work to do these because we don't have any bounds to play with. And so that's what we're going to start with today. In our next lesson, we're going to learn how to deal with the bounds, and that'll be fun. We'll do that then, though. Okay, so one way you could think about this, because a lot of times this can tie your brain in knots. We've been thinking this way for derivatives, now you have to twist your brain and think the other way. If you get confused today, or when you're working on the practice, ask yourself, what expression has this as its derivative? I'd actually like you to pause the video and try that, and try to figure out what function, if you took a derivative of it, would produce this. Or you could write it like this. If this is f prime, what would f have to be? So that when you derivatized it, boom, there you go. Okay, pause the video, try it. Okay, what it would be is that would be x cubed plus 5x. Okay, think about it. If you took a derivative of that, you'd bring the 3 down, subtract 1, 3x squared, boom. If you took a derivative of 5x, you'd get 5, and so there it is. Now there's one little catch. We're going to explain it in a minute. There's actually a plus c on here. Okay, so for right now, just add it. We'll talk about it in a minute. Okay, let's do a couple of examples. Okay, another way you can think about it, when we took derivatives, we did the slide and subtract. If integrals are the opposite of that, or antiderivatives are the opposite of that, instead of slide and subtract, we're just going to do that same thing in reverse. That would be, opposite of subtract is add, opposite of slide won't multiply, so we're going to divide. So it's as simple as this. Take the exponent, add 1 to it, divide by that result. 5 plus 1 is 6. Okay? The exponent here is 1, so we're going to, hey, wait a minute. Did you notice this right here? Those are like terms. We can actually combine those. But we'll deal with that in a second. Okay, so we're going to add 1 and divide by 2. Right here the power is 1. Remember, it's the add and divide rule for integrals. So add 1, divide by, and we're dividing by 2 because 1 plus 1 is 2. Now let's write out what we have. So we have 4/6, that's like 2/3, x to the 6th power, plus 10x squared over 2. Well, 10 over 2 is 5. So 5x squared. And then we have x squared over 2. So minus x squared over 2. We probably need to simplify that. So 2/3 x to the 6th. If we have 5 minus a half, that's 4 1/2, or 9 halves. So we get plus 9 halves x squared. Guys, you got to tack on the plus c. Okay, so put on the plus c at the end. Okay, there's our antiderivative. Let's do this one. If you want to pause the video, go for it. Okay, we're just going to add and divide. Plus 1, 3 plus 1 is 4, so we divide by 4. The exponent's 1, we go plus 1, 1 plus 1 is 2, so we divide by 2. Let's rewrite it. That would be t to the 4th over 4. And 4 divided by 2 is 2, so minus 2t squared. Don't forget the plus c. Done. There's your antiderivative. Let's talk a little bit about why that c has to be there. Okay? And the way I want to do that is I want to think with you about some derivatives. I think this is going to be an accessible way to understand it. So if you had to take the derivative of these, and if you want to pause the video and try it, that would be awesome. The way you would do that is you would slide and subtract. And notice d dx, that means derivatize. We're taking a derivative. Okay? So that becomes 3x squared. What about this one? X cubed becomes 3x squared. What happens to the 4? Derivative of a constant is 0, so it goes away. Derivatize this, 3x squared. What happens to the derivative of negative 5006? Oh, it's a constant, 0, it goes away. What about down here? 3x squared. Derivative of a million, that's 0. Now check this out, y'all. You now have 1, 2, 3, 4 different questions, and in all of them they have the same derivative, or 4 different functions, they all have the same derivative. Okay, interesting. That constant doesn't do anything when you take a derivative. It disappears. And so going back to that question that we talked about a minute ago, what expression has this as its derivative? It's true, x cubed plus 5x would have the derivative of that. But would it also be true that x squared, or x cubed, plus 5x plus 8 would also have 3x squared plus 5 as derivative? Or what if that was 82? Or what if that was 82,357 and we took a derivative of it? Wouldn't we still get that same derivative? We totally would. And so when we write plus c, what we're saying is, you know, I know there was an x cubed and I know there was a 5x, but what I don't know is if there was a constant. So you see it stands for constant. I don't know if there was a constant. And if there was, I don't right now have the ability to tell you what it was, because it might have been 8, or it might have been 82, or it might have been 82,000. I have no idea. Okay? And so that's why we're tacking on the plus c. Okay? Just a couple quick properties. These, by the way, are the same exact properties that we had for derivative, which is so nice that the same properties hold up. All this is saying is if you have a constant in there, if you want to factor it out so it's easier to think about, and see there it is, you're totally allowed to do that. There's an example right here, the 25 is in there. It's hard to see with the 25, so the 25 comes to the outside, and now you can say integral e to the x. Hey, by the way, do you remember what the derivative of e to the x was? Based on that, what do you think the antiderivative of e to the x is? It's its own derivative and its own antiderivative. So what is this? This actually turns into 25 e to the x plus c. Don't forget the plus c. Okay? There's also a sum and difference rule. We were able to do the same exact thing with derivatives. All it says is if, instead of looking at everything at once, if you wanted to break that down and look at each term one piece at a time, you're totally allowed to do that. We've already done that today. We did that here. I looked at one chunk at a time. Okay, we broke it down into a bunch of bite-sized pieces rather than doing it all at once. Okay, that makes it a little easier. Let's do some examples so we can get the hang of this a little better. Okay, so I challenge you to pause the video and try them. If you want to, you might want to write add and divide at the top of the header for this lesson, because until we learn more advanced techniques, that's really all we're doing. We're adding to the exponent, dividing by that result. Let's do it. So I'm just going to put a little plus 1 here. Negative 3 plus 1 would be x to the negative 2. I have to divide by that same thing, and I got to write plus c. Done. That's all it is. Okay. Same with this one. Very, very similar. Remember, the same rules for making it look calculusable from our derivative unit are going to apply here. This looks a little confusing. It's a little easier if I write this as x to the negative second power with respect to x. That dx, by the way, is very similar, I hope you see, to our derivative command. Okay, d dx, integral dx. Okay, derivative with respect to x, integral with respect to x. Okay, that's all it's saying. Okay, so now same thing, add and divide. Add 1, negative 2 plus 1 is negative 1. So I get x to the negative 1 divided by 1. That's the same thing as if I bring that minus up, and don't forget the plus c. Alright? A couple little tricks on these. Again, I really like to encourage you to pause it and try them yourself. That's how you're going to learn the most, so try that. With this, I want to first change the form, writing that as x to the 2/3 dx, and then all the same rules we're talking about apply. Add 1 to the exponent. 2/3 plus 1 is 5/3. Ooh, triple stacker fraction, fun. That means we got to skip, flip, multiply. Let's do that. So now I'm going to have a 3 on top and 5 on bottom, and I'm going to have an x to the 5/3 plus c. Okay, what about here? Okay, 3e to the x, remember, we're going to ignore the constants if they're multiplied. So you could pull that out if you wanted to. I'm not going to. I'm just going to do it directly. That is its own antiderivative. So I get 3e to the x minus, you know what? That looks a little funny. So I'm going to introduce, it's not new notation, but a new way of using this notation that could be helpful. I'm actually not ready to integrate that yet because it doesn't look calculusable to me. And so what I'm going to do is I'm going to say, you know what? I haven't taken an integral of that yet. I'm going to leave the symbol there, and I'm going to rewrite that as 5. Ooh, I can do better than that. I can pull the 5 out. 5x to the -3rd dx, okay? So notice what I'm doing here. Guys, I actually have taken an integral of 3e to the x. I actually have done that, okay? It is its own antiderivative. Okay? It's kind of cool. Okay, so I have done the antiderivative of that. I have not done the antiderivative of that, and that's why I'm leaving those two symbols on there. But now, it's pretty easy to do. Add 1, divide by the result, which is -2. Let's write out our answer. 3e to the x. Okay, minus a negative is going to cancel out. So now that's plus 5 halves x to the -2. Don't forget the plus c. There's your antiderivative. Now, if I were to ask you, how would you know if your answer was right or not? What would you do? What we just did is an integral. How would you check to see if your integral process was correct? You could then take a derivative and see if you get it back out. I want to show you what that looks like with this one. So, yes, this is the final answer. I just want to show you how to check your answer, though, in case you're unsure. Okay, so what we're going to do is we're going to do the slide and subtract. So slide down, and what I get then is 5/3, or slide and subtract. The 5 and 5 would cancel. The 3 and the 3 would cancel. 5/3 minus 1 is 2/3, so I get x to the 2/3. What happens to the c? It's a constant. Derivative of a constant is 0, so that goes away. So I get x to the 2/3 as my derivative. Doesn't that match that exactly? That's how we know that we're right. Okay, and then let's do 2 more, and that'll be enough for today. So check these out. This one is in terms of theta. Don't get freaked out by theta. If you hate it, just in your mind pretend that it's x, okay? X is friendly. We know how to deal with that. We need to learn how to deal with other things as well. Okay, so let's try it. Exponent is 1, so I'm going to add 1 and divide by that result. Ooh, interesting. Okay, this is going to be a little fun with the trig. Now, normally, we take a derivative of sine, that would turn to cosine, but now we're going the opposite way. So what we're asking is, what function has a derivative of sine of theta? A little tricky. Let's see. What about cosine? d theta cosine of theta. What would that be? Cosine turns into negative sine of theta. Okay, so that's not it. We're close though. How could I fix that? I could make that negative cosine, and that would bring a negative here. Minus a negative would be positive. So that means derivative works downward, integral works upward. That means going up the chain, the antiderivative of sine is negative cosine. So what I get then is theta squared over 2. Bring the 2 in, and then I have a minus cosine, or a negative cosine. And so what I'm going to do is I'm going to bring that negative to the front. I'm not going to let it sit in there with extra parentheses and things. I'm going to bring it right here. What did I forget? Plus c. Okay. And there's a little trick for this last one. One thing that could be helpful in this is if you pull the 10 out. Okay, I think you're going to recognize it more easily. So if I rewrite this as 10 times the integral, by the way, when you write those, it's supposed to be a letter S. It's supposed to be a really scripty, beautiful, italicized, mathy letter S. And then I have 1 over x. And so we go back to that question, what function would have a derivative of 1 over x? And guys, I want you to recognize that. Now, if you need to stop and flip back in your notes and find, I want you to do that, because I want you to be able to remember what this is. It's a really easy one to forget, but it's also a really easy one to remember if you get it. So pause the video, go back and find that. What is that? That's a natural log. And so we're going to put natural log of x, the 10 is there, plus c, and there's one little catch to this. You have to put the absolute value bars around it. Okay, and let me show you why. And this is one of the weird little quirks of calculus you kind of have to remember. So it's all about domains. So when I started here, domains, remember that's our input values, what were the values that could have been plugged in for x? So you can plug in any negative number, it's okay to divide by negatives, okay to divide by negatives. Any positive number would be fine, you're okay to divide by positive numbers. The only number that doesn't work here is 0. So the domain of this original thing would be x cannot be 0. Everything else works, all real numbers. Okay? When you write natural log of x, and if you exclude those absolute value bars, what are the numbers that can go in here? Can you put in positive numbers? Sure you can, that's great. Can you put in 0? No. Okay, so that matches. Can you put in negative numbers? You can't. You can't put negatives inside a log. And so the domain of this would be x values that are greater than 0. And that's a problem. We want our antiderivative to have the same domain as our function. So what we do is we slap these absolute value bars on there. And now, if I put a negative number in there, like -7, what happens to it? It goes positive, and now it's okay. So now I'm allowed to put in negative numbers. It doesn't allow me to put in 0, but now the domain of this is x can't be 0. So guys, the way you can remember it is anytime you integrate and you get a natural log, just always slap those absolute value bars in there, and life will be good. Okay? That's all for today. Hope you enjoyed. Until next time, stay mathy.